Welcome back. Here is an important example. Vector space of zero trace 2 by 2 matrices. There's nothing special about 2 by 2. You could have n by n, but any square matrix. Vector space of zero trace. What is the meaning of trace? For any square matrix n by n, its trace is the sum of its diagonal entries. So in the case of 2 by 2, diagonal entries are A and D. You want A plus D to be 0. Trace is the sum of its diagonal entries. I'm looking for 0 trace. Let V be the set of 2 by 2 matrices such that A plus D is 0. That is, its trace is 0. Okay? I hope you'll remember this. Trace means the sum of its diagonal entries. Zero trace is when the trace is 0. Okay? So you have taken a collection of matrices where the entries are all real numbers and A plus D is 0. Okay? Let's define O plus from V cross V to V. O dot from R cross V to V. I hope by now you understand what this means. O plus takes two vectors and gives you one vector. O dot, that is scalar multiplication, takes one scalar and one vector to give you a vector. How do we define it? Standard definition. Take A1, B1, C1, D1, O plus A2, B2, C2, D2, and it is component wise. A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. Okay? Now, how is it closed? Is it closed? So you see we have an unusual set. Now, A1 plus D1 is 0. A2 plus D2 is 0 because they are from V. What about A1 plus A2 plus D1 plus D2? A1 plus A2 plus D1 plus D2. I'm just flipping these two around. I get A1 plus D1 plus A2 plus D2. So this one is 0 because A1 plus D1 is 0. This one is 0 because A2 plus D2 is 0. Okay? So if you take two vectors from this set, their O plus lands again in the same set. So that was closure of vector addition. What about scalar multiplication? RO dot ABCD is RA, RB, RC, RD. So again, coordinate wise. Now, can I get this to be 0? You see, ABCD comes from the vector space. Why should the result land in the vector space? R is real, A1, B1, these are all vectors. Okay, now let's look at the trace RA plus RD. RA plus RD, R comes out A plus D. A plus D is 0 because of this fact that this vector comes from V. So R times 0 is 0. That's why O dot is closed. Okay. So my set V is closed under O plus. My set V is closed under O dot. So closure has been established. Is O plus commutative? Now here on it starts getting standard. If you take two vectors and apply vector addition, you have the expected result. These additions are among real numbers, so that is commutative, right? So I exchange the order, which gets me vector sum of these two vectors. So they got exchanged in order. Is O plus associative? Well, take three vectors, add two of them at a time, wait for the other one. When these two get added, you get this vector. Then you are adding the third vector. You see, this is now each one item, so they remain in parentheses. Okay, the first vector entries are in parentheses. Now this vector goes in. All right. Now this addition is among real numbers. Among real numbers, addition is associative, so the parentheses moved from the left to the right to, okay, in each case, which tells me I can separate out the first entries aside, and this in turn is another sum of two vectors. Okay, there you go. All right, so O plus is associative. What about additive identity? Well, 0, 0, 0, 0 is in V. Why is it in V? Look at its trace. 0 plus 0 is 0. So it is also a zero trace vector. You place it here, and then for any vector A, B, C, D, vector sum, that should be an O plus, with 0, 0, 0 is the same matrix back. Additive inverse. So mind you, that should be an O plus. I will fix it. So take any A, B, C, D in V. You know it is zero trace, that is A plus D is 0. If A plus D is 0, then negative A minus D is negative of A plus D, that's also 0. In other words, negative A, negative B, negative C, negative D is also a zero trace matrix. Notice, inverse should be in your set. It shouldn't be anywhere else. It should be in your set. Once you see that, when you do vector addition, you get the additive identity established previously. Okay, so before I move on to the next page, make sure this is O plus because it is addition of two vectors. So we have established closure and the four addition properties. Now we need to establish the four scalar multiplication property. First one is scalar multiplication is distributive over O plus. One scalar and two vectors because this is O plus. That tells me R O dot, these two vectors get me here, which gets me, you see, R times this, R times this, R times this, and so on. This multiplication is distributive, so R distributes, which in turn I can split the matrix and then eventually get the R out. You see? So R O dot distributed over the O plus. R O dot distributed over the O plus. Now O dot has to be distributive over plus. This is the usual addition. So you need two real numbers and one vector. R plus S, O dot, a matrix. R plus X goes to each entry. Now that multiplication is among reals. So the multiplication distributes, and then I can split along the matrix using matrix addition. Now here I can get the R out using O dot. Here I can get the S out using O dot. That gets me distribution of O dot over usual plus. Is O dot associative, which means I need two scalars and one vector. You see, multiplication, I don't know to multiply two vectors, but I know to multiply two numbers, right? So take RS, O dot, this matrix. This distributes to each piece. This multiplies to each entry. Multiplication among real numbers is associative, so the parentheses move. So now I can first get the R out using O dot and then the S out using O dot. Okay, so S O dot matrix is within parentheses. Last property to check in scalar multiplication, that's the identity. Take the 1 from R, multiply to any matrix, you get the same matrix back. That is, this is a vector space. Okay. Let's come to theorems in our next video. Until then, see you.